Hello and welcome to the third unit in National 5 Chemistry, which is Chemistry in Society. Before I start this unit, I would expect the students to have a good understanding of atomic structure, ions, and isotopes. They should know how to write nuclide reactions as well as they should understand the mechanism of chemical bonding. First topic in this that I'll be talking about today is metals, and we start with metallic bonding. Metallic bonding occurs only in metals. It is a kind of chemical attraction which develops due to attraction between the metal ions and the surrounding sea of electrons. So, before I elaborate on this, I would like to remind you that metals are elements which have either 1, 2, or 3 electrons in their outermost energy shell. And metals have a great tendency to lose these electrons to become stable. So as you can see here, there are two metal atoms which are sodium and electrons present in the outermost energy shell. They are loosely held, and as a result they drift apart from the metal atoms, developing temporary positive charge on the metal atoms, changing them into positive metal ions. These electrons which have drifted away from the metal ions do not belong to any particular metal ion now, and they are said to be as delocalized electrons. So a force of attraction that develops between these positive metal ions as well as the electrons is termed as metallic bonding. Metallic bonding is quite different from covalent bonding as well as ionic bonding. Unlike covalent bonding, which is directional, metallic bonding is not directional because the force acts in all the directions of the positive metal ion. Unlike ionic bonding, where the positive and the negative charges are fixed, metallic bonding electrons, and it is due to the mobility of these electrons that metals have certain specific properties. Talking about the properties, so metals generally have high melting point. This is because of the strong electrostatic force of attraction between the delocalized electrons and the positive metal ions. It is because of this that most of the metals are solid at room temperature. Except mercury, which I would say that is the only exception which is liquid at room temperature, and that is because the force of attraction between the mercury atoms as well as the delocalized electrons is very less, and so less amount of energy is required to break the bond between these positive and negative charges. The next property is that the more the delocalized electrons, the tougher the metals. So if we look at sodium, which has got 281, so it has got one delocalized electron per sodium atom. This is a soft metal. On the other hand, aluminium, which has 283, so this has 3 delocalized electron per aluminium atom, is a tougher metal when compared to sodium. So greater the number of delocalized electrons, tougher the metal. Now, metals are good conductors of heat and electricity. This property is again due to mobile electrons, which have a tendency to carry the heat energy from the hotter end of the metal, that is represented in red color, to the cooler end of the metal, represented in blue color. This energy transfer takes place until energy is uniformly transferred from the hotter end to the cooler end, and as you can see, this is represented by the change of color from blue to red. In the same way, these mobile electrons help to carry electronic charges from one end of the conductor to the other. Since all the metal ions they bond in this way, forming metallic bonding, introducing different metal ion does not disturb the overall structure. So if we look at the structure here, this is representing the parent metal, and these are the ions which have been introduced, right? If so, this phenomenon of introducing different metal ion in the parent structure leads to the formation of alloys. So alloys are mixtures of metals. As you might remember from the mixtures lesson, that all the components of the mixture retain their own properties. Similarly, these two metal ions will have their own properties. Now, if we look at the structure, inner structure, we can see that introducing these metal ions has distorted their regular arrangement of the metal, which was in layers previously, and due to this, these layers cannot move over each other easily, and that makes the structure harder. So, remember that alloys are generally harder as compared to the pure metal. Brass is an example of alloy of copper and zinc, where the copper is which is used in electrical plugs. Zinc adds to the hardness of copper, which is a very good conductor of electricity, and then it is used in making electrical plugs. So now, before we move ahead, let us look at these questions. First question is, which of the following diagrams could be, and what you can do is, you can pause the video, look at the questions here, try to answer them, and then come back to it just to discuss the answers. So the first question is, which of the following diagram could be used to represent the structure of metal? Structure A has positive charges and negative sea of electrons, and B is showing some sort of covalent bonding, C is also showing covalent bonding, and D is ionic bonding. So the answer is A. Yes, that is the correct answer of metallic bonding. Now the second question is also similar to the first one. So it says metallic bonding is a force of attraction between A, positive ions and delocalized electrons, B, negative ions and delocalized electrons, C, negative ions and positive ions, D, a shared pair of electrons and two nuclei. Yes, so the answer would be A, positive ions and delocalized electrons. So I would like to end this lesson here, and before we move on to the next bit, so I would like to end the electrochemical series is a list of metals arranged in rank order of how easily the metal atoms lose electrons present in their last or the outermost energy shell. I have provided you a link of the chemistry data booklet, which contains the electrochemical series and the periodic table that will help you answer questions in this section. But it is good if you understand how to apply your knowledge in answering these questions. So first we'll look into the reactivity table of all the metals. So you can see that on the extreme left hand side there in the table is a list of metals which starts with potassium and goes down to platinum. Potassium is the most reactive metal of all the metals in these series, and platinum is the least reactive metal in the series. So now if we look at, say, first three elements, that is the potassium, sodium and lithium, and let me take you to the periodic table where you can see that potassium, sodium and lithium, they all lie in one group of the periodic table, that is group 1, which means that they all have one electron in their outermost orbit, and they all are lying in different periods of the periodic table. So the similarity is that they all have one electron in their outermost orbit. The difference is that they lie in different periods of the periodic table. And how does this affect its reactivity? If you remember, as we go down the group in a periodic table, reactivity or the tendency of the element to lose electron increases. So, potassium will have a greater tendency to lose its electron as compared to lithium and sodium, and that makes potassium most reactive of all these three elements. So now we have a reason why potassium is most reactive as compared to sodium and lithium. Now let's compare calcium and magnesium. So both calcium and magnesium, they lie in group 2 of periodic table, which means that they have 2 electrons in their outermost orbit. But since calcium lies below magnesium, the tendency to lose these electrons will be higher and greater will be its reactivity. So now I think you can understand why the element potassium is more reactive than sodium and lithium, or calcium is more reactive than magnesium. Remember that the more reactive element will always displace the less reactive element from its salt. Now, as you go down, you come across hydrogen in the reactivity series. Hydrogen is used as a standard here because it is generally found as a positive ion in acids. Say if I take hydrochloric acid, hydrogen is the positive ion there. Sulfuric acid, again hydrogen is the positive ion there. So all the metals lying above hydrogen in the metal activity series can easily displace hydrogen from the acids. But all the metals which are lying below hydrogen in the metal activity series, which are copper, mercury, silver, gold, platinum, they cannot displace hydrogen from the dilute acid since they are less reactive than hydrogen. Now, talking about the reaction of metals with water, we can see that all the elements above aluminium react with water to produce hydrogen gas, and the ones which are below, they don't. Reaction with metals, all the elements above hydrogen have a tendency to react with acid to produce hydrogen gas, but the elements above magnesium are too dangerous to add to an acid because the reaction speed is very fast and it can be difficult to control. Reaction with oxygen. We know that metals react with oxygen forming their respective oxides. So all the metals above, say, mercury can easily react with oxygen forming their respective oxides. So this is how you have to talk about the reactivity of the metals. On the right hand side, you can see there's a mnemonics which will help you remember the order of the metals in the reactivity series. The first alphabet of every word stands for a metal. So please send little Charlie McGregor a zebra. If the lean horse can't munch sweet grass, please. The P in first please stands for potassium, and the P in the last please stands for platinum. So now let's try and test our knowledge and see if we have understood this reactivity series. So you can pause the video here, try and answer the questions, and then come back to it to check your answers. The first is, identify the gas produced when metal reacts with dilute acid. A, carbon dioxide, B, oxygen, C, hydrogen, D, nitrogen. C, hydrogen is the correct answer. Next, identify the metal that does not react with dilute acid. A, sodium, B, calcium, C, zinc, D, copper. Yes, D, copper is the correct answer. Identify the metal found uncombined in the Earth's crust. Now let me remind you here that all the metals which are completely unreactive will be found uncombined in the Earth's crust. So the options are A, gold, B lead, C iron, D sodium. A gold is the correct answer. Now, reaction of metals with water. We know that metals react with water, forming metal hydroxide and releasing hydrogen. So here I have taken an example of calcium reacting with water to give calcium hydroxide and hydrogen. Now the important thing to see here is the state symbols. So S represents that calcium was initially in solid state, water liquid state, and calcium hydroxide has been referred as aqueous because it forms a solution in water and hydrogen in the form of gas. Now look at the ionic equation. So calcium hydroxide in water can be easily dissociated into calcium ions and hydroxide ions. Now remember again that all the metals above aluminium in the reactivity series react with water to form metal hydroxide and hydrogen. Next is reaction with oxygen. Metals react with oxygen to give metal oxide. So we have taken the example of zinc reacting with oxygen to give zinc oxide. So the balanced equation has two atoms of zinc combining with one molecule of oxygen, giving you two molecules of zinc oxide, which can be easily dissociated, forming zinc positive ions and oxygen negative ions. All metals above gold in the reactivity series react with oxygen, forming their respective oxides. Now reaction with dilute acid. Metal reacts with dilute acid, forming salt and hydrogen. So magnesium will react with dilute hydrochloric acid, forming magnesium chloride and hydrogen. So if you look at the equation is again magnesium in solid state reacts with hydrochloric acid in aqueous form, forming magnesium chloride, which is a soluble solution, and hydrogen gas. So when it dissociates, both hydrochloric acid and magnesium chloride dissociate and they form their respective ions. Now in these equations, remember that magnesium and hydrogen, they are all termed as spectator ions because they remain in the same state in the reactant and the product state. So all the metals above hydrogen in the reactivity series react with dilute acids to release hydrogen. Now the question here to test your knowledge is that a student carried out some experiments with 4 metals and their oxides. The results are shown in the table. There are 4 metals, W, X, Y, and Z. Reaction with cold water for W is no reaction. Reaction with dilute acid, no reaction. Effect of heat on metal oxide, no reaction. So I would say that W is the most unreactive element because it doesn't react with any of the 3. X doesn't react with cold water but reacts with dilute acid, which means it is above hydrogen in the metal activity series, and effect of heat on metal oxide says no action. Y, it has got gas produced with cold water, which means that it is above aluminium in metal activity series. It reacts with dilute acid, and effect of heat on metal oxide cannot be broken down, no reaction. Z has got no reaction with cold water, no reaction with dilute acid, but it effect of heat on metal oxide, so metal oxide can be dissociated into metal. Place the 4 metal in the order of their reactivity. So reactivity will be highest in Y because it reacts with cold water, and then there are X produces gas with dilute acid, which means it is above hydrogen, so it will be X, and then Z, it dissociates, its metal oxide dissociates producing metal, which is Z, and W is the most unreactive element. Suggest the names of the metal Y and Z. So you can name any element above aluminium. So let's say it is calcium here, and Z could be any metal which is below hydrogen and above, say, gold or platinum. So it could be copper here. Next, we will be talking about oxidation and reduction. Oxidation, as the name signifies, is gain of oxygen. So you can say that all the reactions in which metals combine with oxygen to form their respective oxides is an example of oxidation reaction. So here's an example of magnesium combining with oxygen to give you magnesium oxide. Now you can pause the video here and try and write the ionic equation for this. So it would be magnesium combining with oxygen to give you magnesium 2 plus and O2 minus. So you can see here that magnesium atom is changing into magnesium ion by losing 2 electrons. So we can say that oxidation is the loss of electrons. Magnesium atom changing into magnesium ion, and it is losing 2 electrons here. On the other hand, reduction is loss of oxygen. So copper oxide combining with hydrogen to form copper in water is showing reduction of copper oxide into copper. So let's do the ionic equation for this. So again, it will be Cu2 plus O2 minus plus hydrogen would give you Cu plus water. So you can see that copper ion is changing into copper atom by gaining 2 electrons. Therefore, reduction can also be defined as gain of electrons. Here you can see that copper is gaining 2 electrons to form copper atom. Redox reactions are reactions where both oxidation and reduction are taking place simultaneously at the same time. So copper oxide combining with carbon giving you copper and carbon dioxide is an example of redox reaction. In this reaction, copper oxide is getting reduced to copper. So let's first do the reduction half of the reaction. So this can be and if you try and balance it, it would be here 4 electrons giving you copper. So it will be 2 times 2. And the next bit is the oxidation half, where carbon combines with oxygen giving you carbon dioxide. So oxidation half would be carbon and if you combine these two reactions, the ionic equation would be Cu2 plus carbon plus 4 electrons giving you 2 copper plus carbon plus 4 electrons, which cancel out each other. So the resulting equation will be 2Cu2 plus giving you 2Cu plus simple displacement are examples of redox reactions. And you have to remember that metals higher in the order of reactivity will be able to displace metals lower in the order. Like you can see here in the example that copper combines with silver nitrate, giving you copper nitrate and releasing silver. Silver we know is lower in the reactivity series as compared to copper. So copper is more reactive and it can easily displace silver from silver nitrate, giving you copper nitrate. So what is happening to copper? Copper is changing into copper ion by losing electrons. It is getting oxidized. Silver ions are changing into silver atoms by gaining electrons. So this is gaining electrons. So this is getting reduced. So you have copper getting oxidized and silver getting reduced. And you can try and write the ionic equations separately and then combine them together. Now, you can pause the video here, try and answer the questions on your own, and then come back to it to check the answers. The first question is the ion electron equation for the oxidation and reduction steps in the reaction between magnesium and silver ions are. So magnesium is changing into magnesium ion by losing electrons. So this is oxidation reaction. So this first bit is your oxidation half, and the second bit is your reduction half. So when you combine these two and balance these two, it will be, this equation will be, can be written as twice Ag plus 2E minus will give you 2Ag. So it will be magnesium plus 2Ag plus giving you magnesium ion and 2Ag. This will be the answer. Zinc displaces copper from copper sulfate solution. The equation for the reaction is zinc plus copper ion plus sulfate ion gives you zinc plus sulfate ion plus copper ion. So circle the spectator ion. Spectator ion is the ion which remains the same on the reactant and the product side. So we can see here that sulfate ion is same on the reactant and product side. So this is the spectator ion. Write the ion electron equation for the oxidation step. So first we have to decide what is getting oxidized. We can see that zinc is changing into zinc ion by losing electrons, and loss of electrons is oxidation. So the oxidation step would be zinc will give you zinc 2 plus 2 electrons, and this is the oxidation step. You can use the data booklet and write it if you want to. The next question is the ion electron equation of titanium changing into titanium ion, and you have to tell whether it is representing reduction of the titanium atoms or reduction of titanium ions, oxidation of titanium atoms or oxidation of titanium ions. So we can see here that titanium is losing electrons. So this is oxidation, and it is oxidation of titanium atoms. We know that the Earth's crust contains metals and metal compounds such as gold, iron oxide, aluminium oxide, and many more. But when found in the earth, these are often mixed with other substances which you may call them as impurities. To be useful, the metals have to be extracted from whatever they are mixed with. So a metallic ore is a naturally occurring rock that contains either metal or metal compound in a high enough concentration to make it economic to extract the metal. The method used to extract a given metal from its ore depends upon reactivity of the metal. So greater the reactivity, more difficult it will be to extract metal from its compound. And stability of the ore, so greater is the stability of the ore, more difficult it will be to decompose the ore to extract a metal. Metals can be extracted from their ore using various methods like passing electricity or heating the ore and then reducing it by carbon or just by the action of heat. So now you can see the electrochemical series here with the most reactive element potassium at the top and least reactive element platinum at the bottom. These metals have been grouped depending on their method of extraction. So you can see that the first four elements, potassium, sodium, magnesium, aluminium, are extracted by electrolysis, in which the metal is dissociated into its ions, and then metal ions, they gain electrons to form metals. The next group, which comprises of zinc, iron, tin, lead, and copper, they are extracted by heating their respective oxides and then reducing it with carbon. So metal oxide plus carbon will give you metal, and carbon changing into carbon dioxide. The last group contains least reactive metals such as mercury, silver, gold, platinum, which can be easily extracted by the action of heat on their respective metal oxides, forming metal and oxygen. So, next we will talk about extraction of aluminium by electrolysis. Electrolysis, as the name signifies, is a process where electricity is used to split apart the compound into its respective ions. And remember that it is a redox reaction, which means that both reduction and oxidation take place simultaneously in the same reaction. So here you can see a setup in which we have an electrolytic tank and two electrodes, positive electrode as anode and negative electrode as cathode. They both are made up of graphite, and you can see that cathode is lining the tank, whereas graphite electrodes is present in the form of metallic chips. Both the electrodes are connected to a cheap source of electricity. And the tank contains molten aluminium oxide. So this is the ore for aluminium. Remember that whenever you talk about extraction, you need to have information about which are the ores present in the Earth's crust for that respective element. So aluminium is generally found in the form of its ore, alumina. And alumina is nothing but Al2O3, that is aluminium oxide. When electricity is passed through this channel, then aluminium oxide, it tends to dissociate or split into its respective ions, which is aluminium and oxygen. So aluminium is the positive ion and oxygen is the negative ion. So what happens is electricity has split the compound into its respective ions. The positive metal ions, they migrate to the negative electrode cathode, and here they would gain electrons to form pure aluminium metal, which is deposited at the bottom of the tank. On the other hand, oxygen would move to anode, where it would lose electrons and undergo oxidation. These atoms of oxygen will then combine to form molecular oxygen, which can be released from anode. And the metal deposited on the negative electrode is 99.9% pure. Next, we will talk about extraction of iron. And as you remember, iron comes in the second group, where generally metal oxide is heated with carbon to extract the respective metal. So we are extracting iron by using carbon. And for this, we need a blast furnace. So as you can see in this figure, we have a blast furnace here. And this blast furnace is fed from the top with coke, which is the pure form of carbon, iron oxide, which is ore of iron, and it is represented by the formula Fe2O3. Limestone, calcium carbonate. This is added to remove acidic impurities from iron by reacting with them to form molten slag, which gets deposited at the bottom of the blast furnace. Now, the reaction in the blast furnace takes place in 3 stages. To start with, blast of air is passed from the bottom of the blast furnace. air combines with carbon to form carbon dioxide. Now this carbon dioxide, it moves up where it meets with carbon coming from the top and gets reduced. So carbon dioxide plus carbon will give you carbon monoxide. In the third stage, carbon monoxide combines with iron oxide. So we have Fe2O3 plus carbon monoxide giving you pure iron and carbon dioxide. Iron being heavier, it moves down and gets collected at the bottom of the blast furnace in molten state from where it can be easily removed. And carbon dioxide, it moves up and it gets released in the form of waste gases. So these are the reactions and these are the stages in the blast furnace which help to extract iron. Now we have a word bank which consists of words which you need to fill in the blanks of the ion electron equations that I have provided you here. So what you can do is pause the video, try and fill in the blanks and then come back and check your answers. So let's see what the answers should be here. The oxygen ions in solution lose electrons forming oxygen atoms. We see these as gas at the positive electrode. The aluminium ions in solution gain electrons forming aluminium atoms. We see these as solid at the negative electrode. So now you can see the equations that are taking place at anode and cathode. So next we will talk about the percentage composition of ores. As I said to you before, that a metal ore is a rock containing a metal or metal compound in a high enough concentration to make it economic to extract the metal. So it is very useful for scientists to be able to calculate exactly what proportion of any metal ore is actually the desirable metal. So typically, giving you an example of iron, which exists in various ores like iron sulfide, so this could be written as FeS, iron oxide, which is written as FeO, and iron 3 oxide, so this is written as Fe2O3. We will try and calculate the percentage composition and see which is the best quality of iron ore from where we can extract maximum iron. Will provide an easy way to compare the iron content and thus to decide which will be the most economical ore to go with. So now let's see the percentage of iron in iron sulfide. So iron sulfide has one atom of iron which weighs 56 atomic mass units, one atom of sulfur that weighs 32 atomic mass unit. So the total molecular mass would be 88 and the percentage of iron is 63.63%. Now ferrous oxide has one atom of iron and one atom of oxygen. So the total molecular mass would be 72 and the percentage of iron in this would be 77.78%. The last is ferric oxide, which has 2 atoms of iron and 3 atoms of oxygen. Total molar mass is 160, so the percentage of iron is 70%. So of the 3 ores, we can say that it is most economical to extract iron from ferrous oxide because that contains maximum percentage of iron or maximum iron content in its ore. Now, to test our knowledge, we have few questions. So again, you can pause the video here, try and answer these questions and come back to check your answers. So the first question is, which of the following metal can be extracted from its oxide by heat alone? So remember that those metals which are less reactive and which lie in the third group, which we had divided based on the electrochemical series. So A is aluminium, B is iron, C silver, and D zinc. So the answer would be C. Metals can be extracted from their ores by different methods. Place the following methods in the correct space in the table. For mercury, it will be heat alone, iron reacting with carbon, and for magnesium it will be electrolysis. Mercury can be extracted from the ore cinnabar. Calculate the percentage by mass of mercury. So cinnabar has 1 atom of mercury, and if you go back to the data booklet, you can see that the atomic mass of mercury would be 201. 1 atom of sulfur, 32. So the total molecular mass would be 233, and percentage of mercury in HGS would be 201 divided by 233 times 100, and this gives you 86.26%. Write the formula of mercury ion in cinnabar. So HGS would dissociate, giving you Hg2 plus S2 minus. So this is the formula for mercury ion in this, and this mercury ion would gain 2 electrons to give pure mercury.